Hi, I'm Brendan, and this is Avoiding Performance and Design Pitfalls with Unity. Who am I? Well, I first worked with Unity at an iPhone game studio back in 2008. Since then, I've worked with many of the platforms that Unity supports, both console and mobile, under heavy performance constraints. Most recently, I've worked with Oddworld Inhabitants and Titanium Studios on Oddworld Soulstorm, which is, as far as I'm aware, one of the largest Unity titles ever made. Currently, I'm still in Perth working at Viewport, which is a games-adjacent studio doing AR and VR projects. Engineering is all about trade-offs. There are few one-size-fits-all solutions. It's tempting to say that Unity sucks for X, or Unity sucks for my game, but the reality is, Unity is intended to be a general game engine. The built-in solutions will get you part of the way there, especially for prototyping, but some of these systems, your game will stress some of these systems in ways that they weren't designed for. No one knows your game like you do. So you want to figure out early where Unity systems will be inadequate and look at how you can build your own, or use Unity systems in ways that will fit inside your performance envelope. You need to pick your battles, especially in the indie space. You can't do everything as much as you'd like to, and you have to concentrate on what's going to give you the best bang for your buck. With that said, here are the things we're going to talk about today. We're going to start our journey talking about the implementation of a custom component lifecycle, specifically in relation to Unity's loading system. I'll give an overview about how Unity loads scenes, provide a metaphor for how a frame works and why you need time slicing, and then go through some implementation details for a custom lifecycle that does time-sliced scene activation. This leads us to an often overlooked feature of Unity, custom event loops, which is the ability to manipulate Unity's game loop. I'll talk about how this works and provide some concrete examples of how this would help the custom lifecycle in section 1. Then we'll take a short trip into rendering land, talking about how to get the most out of Unity's culling system, why static batching can cause memory issues, and some tips about read batching and branching in shaders. Then we'll take a look at what happens when you try to get more people on your team with respect to level design and Unity's scene infrastructure. There are some issues you're going to encounter with what Unity gives you, and there are different ways of solving this. We'll talk about the elephant in the room, and that's cross-scene references, which exists out there and what problems you may encounter with that sort of system. Animation is something most games need to do, but Mechanim has some things you need to keep in mind if you're going to be animating large numbers of characters. There's also other options than Mechanim here. You can't get save load in early enough. I'll talk about issues that I've encountered with save load, but every time we don't do it early enough. So please keep this in mind. With that said, let's go on to the custom component lifecycle. When Unity first got asynchronous loading, we thought that we could simply start using multiple scenes to break our games apart and load them in the background at low priority, and Unity would handle everything and it would be sweet. And for the most part, this works. But there's a big caveat. Every time we get to the end of a load and have to activate the scene, it stops. What's happening? Unity has to go through two major phases. First, it needs to get the scene resources into the system and GPU memory, and for the most part, this can be done in the background without affecting your main thread. However, Unity then needs to activate the entire scene graph, and this is where problems arise. It's going to try and do all of that work in one frame. Everyone's probably pretty familiar with the monobehavior lifecycle. What Unity is going to do for activation is call all these lifecycle methods in one frame, and that's inevitably going to stall. It's going to activate all your game objects, it's going to enable the monobehaviors, call awake, enable, and start. All of this in one frame. So a good analogy for what's going on is a dining experience. The guests are monobehaviors themselves, the tables are game objects containing the monobehaviors, and the kitchen staff are Unity's main thread. All the guests must be seated before any guest can get any food, as in we have to activate the game objects before we can wake up the monobehaviors attached to them. Everyone must eat a single course before they can start a next course, otherwise it's unfair. And these courses are the monobehavior lifecycle callbacks. And once everyone's fed, then everything's activated. So Unity's default diming experience involves all the scene activation dimers just jamming into the line without regard for the other diners the kitchen staff have to serve. They're like the boomers of the main thread. The staff then get overloaded serving only these diners until they're done, and they have no time to service the other diners, the other tasks, causing frame drops. So we need a method to ensure that the kitchen can pause serving these diners. So we have to remember that each frame the kitchen staff can only do so much. If we're trying to activate a scene while rendering a game frame, we may not want to serve the activation diners first. Instead, we may actually want to serve them last. So we need to split them off into their own queue, and we can deal with them later. After each activation dyno is served, we have to check how much time we have left so we don't exceed our frame time. We may need to come back to that point later on. So this general idea will not cause a frame stall, and we can still activate the scene mostly how we're normally used to. So how do we go about doing this? First, we need to disable Unity's activation step for most of our game objects and mono behavior, but we don't want to present a foreign experience for our designers, so we're going to need to add some hooks to the editor. You'll need to hook into editor scene manager.scene saving and scan a scene for active game objects and mono behaviors, and you'll have to save these in a list somewhere. The list needs to be somewhere that you can access from the runtime lifecycle activation system. Ideally, you'll want these lists sorted in the order that they're going to need to be activated in. To preserve Unity's usual editor behavior, you're going to need to add another hook to editor scene manager.sceneOpened so that it restores these states. That way, your designers will be presented with their usual Unity experience. That handles edit mode, but it won't handle play mode or your runtime. I strongly suggest that, even though it will harm your iteration slightly, that you go through the same disable/runtime manager setup when entering play mode as you will in runtime. The reason for this is it ensures your designers and engineers are dealing with the same system in editor that they're going to when the game is released. Now you have a situation where you either have very few or no objects to activate. So the Unity system will take very, very little time. And one thing to remember about this whole system is that your wall clock time is going to be longer than doing all the activations at once. And this is because there's going to be slack time at the end of every frame, and you're having to wait for the frame render. So if you're looking for absolute fastest load time, this isn't going to work for you. However, most of us don't necessarily need absolute fastest load time. What we want is to continue presenting the user with a gameplay experience while we're loading new things in the background. So this is fine. Also, while this time-sliced activation is occurring, you're going to have to be careful because some of your mono behaviors are going to be active and running while other ones haven't yet been activated. So you need to be careful about race conditions in this state. So some implementation tips on doing this system for yourself. You'll need a base class that you can inherit from for your lifecycle system, and this class is going to need custom lifecycle methods to avoid unities. So obviously these are silly names, but that's what you're looking at. You'll need to record your frame start time somewhere very early in the frame, or in a custom event loop callback. We'll talk about those in a sec. Then close to the end of the frame, after rendering's been sent preferably, you'll want to process your activation callbacks to that frame. If there are any inactive game objects, you want to activate those. Then you want to run your custom awake behavior and then your custom awake method or your custom start method. After each step, so after a single game object or calling a single one of those methods, you need to check your time left. If you're out of time, pause there, resume next frame. So what are our takeaways here? It's important to remember that Unity's default activation system will, in one frame, activate all of the active game objects, enable all mono behaviors, calling awake, enable, and start at least, probably update as well, in one frame. That's going to cause load spikes. Fixing this is a little complicated, but totally doable. And you're going to want to keep your play mode experience as similar to runtime. That way, you're going to debug in the editor where it's a lot easier. And now we're going to talk about Unity's custom event loops. So in 2018.1, Unity added the ability to modify the event loop. The default loop is a PlayerLoop system, and these can be nested. Here's the default Unity loop, which has the major phases. And those are all PlayerLoop systems themselves, and they have subsystems, which are all of these. I've expanded those subsystems in fixed update, pre-update, and update, and all of those are themselves PlayerLoop systems. It's PlayerLoop systems all the way down. A PlayerLoop system consists of the following: a subsystem list, which is an array of PlayerLoop systems, callback functions, and those are either a C# function using an update delegate, or there's a native pointer function. The documentation implies that this will only work with Unity's native functions. I've not tried to write our own methods, so your mileage may vary here. You can have both callbacks and subsystems in a PlayerLoop system. Unity's going to call the callbacks first, and then it's going to iterate through all of the subsystems in the array order. So how do you make this your own? You need to get the default loop and modify it, unless you need absolutely no native Unity functions. At which point I question the utility of using the Unity game engine. Whatever. You can, however, modify and remove entire frame phases. Don't need Unity physics? Get rid of it. You can add new subsystems at any level or to the top level loop, adding entirely new phases. You will need to do this every time the assemblies are reloaded, so you'll need to do this early in your game's initialization process and in the editor as part of transitioning into play mode, assuming you have to reload assemblies. If we take our previous example in section 1, we could add a subsystem with a callback to the time update player loop system and use that to record our frame start time. Then we add another one to the post late update right at the end to actually perform the time sliced activations, thus ensuring that you're getting the exact start of the frame and you're running after all the other work in the frame is completed. So what are our takeaways here? You can modify Unity's default event loop. It's all player loop subsystems, so it's really easy to understand. And you can remove subsystems that Unity has that you don't need. Let's dive into rendering. So, caveat emptor, disclaimer. These are from my experiences with the Unity standard pipeline as of 2018/2020. I've not used URP on a large project yet, and I've never used HDRP. I've looked at the pretty examples, I've kicked the tires, not on a project yet. There might be magical fixes for all of these things, especially culling, in these new pipelines. But with that said, the built-in Unity color is only really designed for non-static render accounts in the low thousands. Every active renderer not handled needs to be evaluated by the color during the render loop, and this can take a surprising amount of time, especially on console platforms. If you have these kinds of render accounts, you're going to want to pre-cull pretty aggressively. Unity has a built-in system for doing this, but I've never had much success with it. If you can use it, it's built in, use it. Otherwise, you're going to need a custom system. You're going to want to think about how your game works to do this. If you've got a platformer, you could probably take advantage of the fact that you'll be focused on one part of the level, and then you can pre-cull the other parts that you're not looking at this current time. If you're in VR or you're doing first or third person games, maybe if you're inside a room, you can pre-cull everything outside of that area. If you're outside, I don't have any good ideas for you. Sorry, never built an open world game. This is, however, one of those really game-specific things. Different games are going to have different requirements around the view frustum, so just think about that when you're planning. Simply disabling the renderer itself is sufficient to remove it from consideration by the color part of the render loop. So that means you can continue to run game objects, like game logic, on your mono behaviors and game objects while disabling their renderers and excluding them from the color. So that's useful to know. Let's talk about static batching. So we enable the static flag and use static batching, usually to get more rendering performance. It's great. The geometry performance is vastly improved on our background level props. But there's a downside, which is obvious in hindsight, but it wasn't obvious to me before I encountered it. It's actually quite bad for memory. What Unity's doing is it's taking all those unique meshes and combining them to as many big chunks as it can, removing any possibility of instancing or referencing the same mesh models. This will balloon your GPU requirements if you're using a lot of different objects. And it can be especially bad if you use clutter-based game level design, which a lot of games are doing because it's a really rapid way to get a level out. So be aware of that and do some profiling. This will be especially painful on your last generation console platforms. So shader optimization. Let's take a look at reads. So you want to make use of any empty channels you've got to optimize reads. If you're already reading a texture and you've got a spare channel, pack some more data in there. For example, if you're using Unity's standard shader and you have a constant metallic or smoothness map, you should take the one that's not constant and pack it into your RGB map, the albedo channel, or the albedo's alpha channel. And then you use a constant for the one that's constant. That's going to result in far less reads, usually about a third less. One caveat with combining reads though, you can only do this if you're reading from the same location. So if you want to pack an ambient occlusion texture into an alpha and albedo, this is not usually a good idea because your ambient occlusion map's going to read from UV1 and UV0 and you're going to instead be reading in red, green, and blue when you don't need it on a pixel from that texture. So just be aware of that too. Historically, the advice on branching in shaders is don't, but modern hardware makes it more complex than just that. Broadly speaking, there are three kinds of branching at the moment. There's a compile time static variable that's used to branch. That can be problematic from memory perspective because it's going to result in more variance of that shader being compiled. But in terms of performance, in terms of fill rate performance, it's fine. You can have a branch based on a uniform variable, a variable that's the same for every single texel that's being generated on that particular pass. That's great, that's fine. They'll take one pass, most modern GPU hardware can do this with no trouble at all. Then there's full dynamic branching, and that's where a given texel can take a different path within the same pass. That one is not so fine. GPU schedulers are not designed to deal with this. They like lots of batches of operations that take exactly the same amount of time. It's how they work. They're massively parallel computers. So you still want to avoid those ones. So what are our takeaways for rendering? If you've got a large number of renderers, beware the culling time and pre-cull aggressively. Static batching, you have to check your memory because it can use memory and you may not get the wins you need. You want to combine reads on shaders where possible. That'll accelerate your fill rate. And only worry about full dynamic shader branches. You may want to convert your compile time variables to uniforms if you're compiling too many shader variants. Let's talk about level design at scale. So let's talk about workflows. As engineers, we've got a bunch of useful tools to allow multiple engineers to work on a project in parallel. Source control systems were made by and for engineers. While analyzing source code to resolve merges isn't a solved problem, we have a lot of tools to make it easier. Merging Unity scenes, however, even with YAML merge, is extremely painful. If YAML merge fails, it's very hard to figure out what goes where without comparing the scenes in Unity itself. Even hooking up YAML merge can be tricky for engineers, let alone less technical members of your team. As the number of people working on the project grows, especially in engineering and design, stopping these merge conflicts is very tricky. This is compounded by the fact that Unity has no way of serializing and deserializing cross-scene references. This is to do with how projects are built and how Unity doesn't have a deterministic system for figuring out what a Unity object ID is going to be until it's built. Here are some options I've experienced and their drawbacks. These solutions aren't really mutually exclusive either. You can do some sort of locking, thus avoiding the entire merge problem. You can separate those scenes out, allowing less contention and less merges. And then you don't need but you may not necessarily need to go to cross-scene references by doing that. Or you could go the whole hog and implement some sort of cross-scene reference system. Let's go through these each individually. Locking the scene is the most straightforward solution. The pros are the tooling's pretty easy. If you're using Subversion, Perforate, or GIF LFS, you've already got locking, and all you need is a way of exposing those locks in the Unity UI so your developers know not to touch a locked scene file. It's also pretty easy to expose this using other mechanisms, for example, your chat system via bots or something else. You could even have a duck that people could hold. The engineering effort is very small. All the systems you have to use are at edit time only, and they're very straightforward systems. There are no runtime requirements for this, so it's pretty unlikely it's going to cause any bugs in your game. The cons, however, there is some workload overhead. You're going to have to ensure or provide tools to ensure that everyone is locking their files before they do modifications. It's pretty easy to forget to do this, make a bunch of changes, then someone else has locked the file before you've committed, and now your changes are going to be lost, or you're going to annoy them saying they have to get your changes. There's also resource contention issues as a result of this. If there are any scenes that require a lot of changes, or a particular developer needs to iterate on a particular scene, or needs to, in the worst case, perform a bunch of modifications, it can easily block other developers' work. That leads us to the next solution. You can split up scene files by concern and use engineering to solve some of the issues that may arise. There's an obvious application for this, and that's splitting your user interface off from everything else. The pros for this include that the tooling is probably something that you already have. If you have any kind of dependency framework or some sort of manager system, then using that as a message passing system between scenes, it's relatively easy. Message passing systems are pretty straightforward. There is some runtime engineering effort that'll need to go in for the additive scene load, but in most cases, those are pretty straightforward, and your message passing systems are extremely battle tested because you use them everywhere else in your game. It can reduce contention by doing this because by splitting your files up into separate concerns, then someone who's a UI designer will not need to touch your levels, and the level designers and your UI designers can now work in parallel. However, there are still some cons. You will need some runtime and possibly edit time way of additively loading these scenes because Unity doesn't provide anything to do this by default. And that's because there are wildly different ways to use the multi-scene system that Unity has. And as with any new system, there's the potential for bugs here, but it's still a relatively simple system to engineer, and it's unlikely to have bugs. And there's only so much things you can split off using this method. It's tricky to expose deep integrations between scenes using this mechanism, or scenes that your designers can use. You could make more complicated hooks, but the more complex those hooks are, the more complex the system, the more bugs that are likely to have. As an aside, one of the spaces where this is actually really useful is in VR titles as a UI abstraction system. There are still a lot of headsets that don't use the same API, but what you could use is you could have a interface scene that is designed for each particular headset, for example, Oculus Quest, PlayStation VR. And then they act as an interface to the rest of the game. So you could have your levels, and they're exactly the same for all headsets, but you don't have to worry about data for one headset when you're running another headset. It's a really useful method. I've used this very successfully on many titles since the first one we shipped on VR. Finally, that brings us to the ultimate, cross-scene loading. So the pros are amazing when it works. You can break your scenes into sub-scenes pretty fine-grainedly, allowing massive flexibility in workflows. And when done right, this is almost invisible to your developers. However, this is not a simple system to implement. You have to hook into Unity save and load, and you have to do it in a pretty dramatic way, and you have to bake the scenes into one scene at runtime, or have runtime versions of the reference restoration code. Because it's a fairly big system touching an editor and runtime, there's a large surface for bugs to occur. Incorrectly serialized references can fail to restore, you can lose designers' work, and you can cause some very hard to track bugs. I've run into these, it's not pretty. It still requires planning. You can't just jump into cross-scene references and expect your contention issues to go away. You have to figure out how your workflows work and make sure that your scenes are split such that different departments only need to access single scenes. As an engineer, you need to think about where you bake your static data, because if you bake that into a scene a level designer needs to touch, it's not going to be obvious to him whether his changes actually require committing or not. And then you're back to the same place with merging. So there are two main implementations of cross-scene loading that I know of. One I've used extensively, and the other was written for System Shock 3. Take from that what you will. Advanced multi-scene seems to be the go-to. It's a $35 per seat asset. I've heard a lot of good things, historically. However, the project I was working on that used it had many strange bugs that were caused by this system, which is how I know what the pitfalls of cross-scene referencing are. It also looks a little bit like it's been unmaintained since last October, and I'm seeing forum posts from more recent Unity versions complaining that it doesn't work properly. Your mileage may vary. William Armstrong from Unity has a talk entitled Cross-Scene References, a Shock to the System. It's well worth a look. It explains the issues and his solution in far more detail than I can here. The code itself is available on GitHub for free. I've not personally battle tested this framework, but in theory, during what pre-production and production happened on System Shock 3, I'd hope it was fairly well battle tested. Regardless of what you do, ensure that you stress this system very hard, very early in your project, so that you can course correct if there's an issue. So what are our takeaways from level design at scale? Unity's solutions are not good, not for level design at scale, not for a team size that gets larger. But you want to use the minimum cost engineering solution for your game team size. If you have 5 people, there's one level designer and there's one UI designer, sounds like just breaking them up into separate scenes is a great solution there. If you've got multiple level designers, can you break them up by level and then just do that? Each level is a scene? That sounds great. Don't need cross-scene loading. If you have a sound designer who needs to touch all of your levels and level designers that need to touch all your levels and your team starts to get into the 5 to 10 designer range, you're probably going to have to bite the bullet and go for cross-scene referencing. Before you do this, design your workflows around what you can do. Battle test the tech, see what your workflows are, make sure they match. It's going to be different for each project. And whatever cross-scene solution you use, test. Make sure that it doesn't cause bugs. The worst kind of bugs to cause you are either gameplay breaking bugs or bugs that the designers are going to call you up at midnight about. Battle test everywhere you can. Let's talk about animation. By default, in Unity, you have 2 built-in animation systems, Mechanim and Legacy. It's a pretty open secret by now that Mechanim isn't the fastest animation system in a game engine, but there are a few things that can make it particularly slow. One is using the humanoid rig. Unless you need IK or mesh retargeting, avoid it. Even if you don't use these features, it can take up to 25% longer than the generic rig does. Mechanim can also do some of its work in parallel, but we can only do this if it detects that each animation is occurring in a different tree. We saw some massive gains by moving all of our animated characters to the root of the scene, and this allowed them to all run in parallel. You may not have to move it to the root, but we found that that was the most effective way of ensuring they were running in parallel. Nowadays, we may avoid the legacy animation system, as it doesn't provide the feature set of Mechanim. But it's also important to notice that it is single-threaded, unlike some parts of Mechanim. Despite this, it's surprisingly fast, especially for simple animations like door opening and closing. If you can handle writing your own simple state machine to drive it, it's probably worth looking at for these kinds of animations, as it will be faster than using Mechanim. Another option is to use what I'm calling Flipbook animation, which is a total blast from the past. What you do is you pre-bake the frames as mesh data and flip through them, kind of like how you'd use a sprite book. It's very, very fast to do, as you're just changing which mesh you draw each frame for each character instance. It is quite memory hungry, as you need all of those meshes loaded into memory. If you have the same animation playing on many, many characters, only offset by the frame number, it's very efficient to use. You can also animate your objects via Vertex Shader if you have spare geometry processing time. It's a great option. It's perfect for simple animations, and we used it on Symphony of the Machine quite effectively to have objects bob up and down in space. Saved us much time over trying to do this in Mechanim, or even simple animation. You can do quite complicated effects such as cloth if you're willing to spend the time on it. And a good case of looking at this is the cloaks in Destiny. They are, as far as I'm aware, done entirely by Vertex Shaders. So what are our takeaways here? You should use legacy animations for simple animation tasks. You should avoid humanoid rigs unless you really need their specific features. And you have other options, but they're going to require a little bit more work. Let's talk about save load systems. Almost all games are going to need to do some form of save load. Unless your game has no preference system or saves any state between sessions of game, you're going to need to have some sort of system for this. And if your game has any kind of large audience, bugs in these systems are going to get noticed by players. Any bug that loses progression is a potential user who's going to stop playing your game at that point. The complexity is going to scale with the amount of state that you're saving. This is like most systems, but it's especially pernicious in save games. And if you're tracking entity state in particular, like positions in a level of everything, it's going to get very complex indeed. However, getting it in can be really useful for debugging, as you've got a snapshot that you can run so that your QA department can send you a snapshot, and then you can use that to reproduce bugs. It's really useful. For all of these reasons and more, I strongly suggest that you want to get that in as early as possible, and that you stress test it constantly throughout your game development process. It's also super important to make it clear to your testers about what is a valid bug report and when. If you don't have a particular feature in your save load system working at the beginning and you don't want them to test it, that's relatively fine, but make it very, very clear when that state changes, and you should change that as early as possible. Again, you want a fully functional save load system as early in your production, and you want to enable your bug department to report bugs to you. If you do have a save load system, you're going to need to think about patching the game. At a minimum, you're probably going to need to have some sort of data migration framework for at least some of the data in your save game system. It's very likely that you're going to want to add fields, or you're going to need to add updated fields because of new features or other fixes you're going to perform on your game. And it's essential that you can cleanly move. You can also do this by allowing the game to load an old version of the game and then change it in memory. It's useful to enable these as early as possible in your development cycle, even as you're adding features as you produce the game, as it will enable these migrations or old save loads to be tested by your QA department, and then they don't have to constantly blow away their progress. If you're storing data that designers can change and will change the meaning of the game with a patch, you have to think about how this will work. Let's look at an example. So say your game is based on conversations, and you have a number of conversations, and you store the state of you store the result of a conversation and what conversation the player is at. If there was an important conversation that they moved from later in the game to earlier in the game, but your players are now past this conversation, they'll not encounter this conversation in that game run through. And you have to think about how you would handle this. This isn't strictly a data migration problem, as it interacts with design. And the more data you store, like all the entities in a level, the harder this question gets. So you have to think very carefully about it. There's going to be communication and validation issues every time you make these kinds of changes, both in your team and external parties. There's always a risk that there might be loss of progress, and how do you communicate this to the players? Is it worth making changes that will automatically allow you to identify these kinds of changes and either prevent them or communicate to some person in your customer relations department that can detail these to the players? Can you identify ways of mitigating them in advance? These changes have QA overhead, and this is very tricky. They want to have, as an engineer, you want to have a good set of save games that exercise all the migrations that are going to occur, but that's additional overhead for QA to test those. And your QA department, especially in an indie game, is already busy, and this is going to add to their overhead. In addition to all of this, the console platforms that you work with, especially the partners, Microsoft, Sony, and Nintendo, have requirements around patches and losing player progress data. They're going to be extremely annoyed if you lose progress data, and they may fail your patch. So be aware of this. I don't have any simple solutions. This is one of the places especially where there are no simple answers and it's hugely game dependent. I would think about having some sort of emergency fallback data set or an emergency fallback save game. Maybe save an older game that they can return to, or have like a minimum viable set that has good migrations that will always move forward. You're going to lose progress, but you're going to lose less of the player progression, and hopefully they won't mind and they will keep playing. You could also simply store less data. You could basically say, instead of saving during a level, you can only save at the beginning of a level. Or you can make sure that your level can restart at any given checkpoint, and all that matters is the checkpoint that you start at. These are little and simple and obvious, but you'd be surprised at how many AAA games actually get away with this method. If you don't have to save it, don't save it. If your game has good telemetry, you can fire back data if there's a failed migration. And while this may not help in certain cases where the migration fails but produces semantically inaccurate data, it can still give you something to work with if you've got a bug that's reached the field, and you can hopefully mitigate it with this. In that case, it's probably worth sending the save game data back, but be aware about privacy concerns around this. It's also useful to have this kind of telemetry because if you're going to change a level and players are going to lose progress, you can see how many players are in that level and then design around that constraint. Whatever solution you go with, if you have a large number of designers or they're non-technical, asking them to know when a change that they're making will invalidate your game state is probably not going to be tenable. You need to make a set of rules that they can look at before doing a change once you're past release, or you need to make some sort of tooling with validations that will allow this check to automatically happen for them. It's worth investing in this up front if you're going to need it. Obviously, the ideal world is we avoid making these kinds of changes. Unfortunately, that doesn't always happen. So what are our takeaways? Test early, test often. Out of all of the systems I've talked about, save load is the most important to stress because it is in a lot of ways the most visible to your player. Try and keep the minimum viable save state. The less state you store, the less complex this system is. So maybe just design around the constraint. And be aware of those console requirements. They do really get annoyed with you if you lose player data, so try not to do it. Overall, planning is key. For almost every issue that I've raised, it's going to affect your workflows, it's going to affect how your production goes, so plan in ahead. Work with the producers and leads during the pre-production and production stages and ensure that you're delivering value in the right places and that the workflows are working for everybody. Don't be afraid to go for simpler solutions if your game design doesn't have the complexity required. Ensure you've left enough time to stress test complex systems before they get used too deeply, or stress test any major modifications you make of Unity. You don't want to get too deep in saying you need to save the entire game state and then discover your system isn't going to work. Focus on the systems that make your game special. You might not need background loading. It might be fine for your players to wait for that. Great, then you can avoid a whole bunch of complexity with that system. Design and production can help you work out where to spend your time here, so take their advice and work with them. There'll be a short QA following this, so if you've got any specific questions, you can ask there if this video is being watched during GCAP. Otherwise, you can get in touch with me at the following places. And if you want to see what I'm working now and what I'm working on, check out Viewport's site and the LinkedIn there. Thanks very much.